Dear participants of the 15th SDEWES conference, which was planned to be held in Cologne, but because of coronavirus, we are having it online. I would like to welcome you to our third invited lecture. Recently, I met Professor Henrik Wenzel. I was opposing his PhD student, which fortunately managed to answer all my difficult questions because it was obviously so well led by Professor Wenzel. And it was a very interesting experience for me. Today, Professor Henrik Wenzel will give a lecture on extremely important scientific problem, how to solve the remaining part of the energy transition, because we will need some fuels and we want to make them renewable. Professor Henrik Wenzel is head of the Life Cycle Engineering Center at University of Southern Denmark and professor of Life Cycle Engineering and Environmental System Analysis. He is a member of the Danish Bioeconomy Advisory Board for the government, the Independent Research Fund Denmark, and the Technical Advisor Board of the Waste and Resource Network Denmark. He has 30 years of experience in system analysis, including life cycle assessment, energy system analysis, resource criticality assessment, and socioeconomic analysis. And he has studied energy systems and energy technologies in the systems perspective for 20 years. Most recently, his work has centered around electrofuel technologies and their integration into the energy system, and he has studied sustainable aviation fuel supply pathways in collaboration with key stakeholders from the aviation sector, including chairing the work on sustainable fuels with the recent aviation sector climate partnership in Denmark. He will present today the latest finding from the Nordic project on the jet fuel from the gas to liquid pathway and the status of the aviation sector electrofuels strategy. So, Henrik, floor is yours, or shall I say screen is yours.
Yeah, thank you very much, and thank you for the kind introduction. Yeah, I'm going to talk about what is called Power to X, or electrofuels, as Nevin said. And this is as a specific version of that, namely the gas to liquid pathway, where biomethane as well as CO2 and hydrogen can be the feedstock. But I'm going to talk as well about the role that such a pathway has in the energy system. Because producing the final fuels that we need, the liquid fuels for aviation and long distance sea transport and the heaviest trucks, etc., those fuels that we cannot, where we cannot electrify those energy services. It is not only a fuel production, it's also the final means of being the last piece in the puzzle of the energy system, a system integrator that can help balancing the fluctuating electricity production, etc., etc. So I'm going to show that. I have Anders Winter Mortensen on the front page here as a co-presenter of, co-producer of the slides, because that is the PhD student that Nevin was referring to in the beginning. Now my former PhD student, and this is part of his work as well. So let me begin. As many of you might know, Denmark has a long-term energy policy goal of being fully renewable by 2050, and we've had that for the last 4 consecutive governments. Both the right and the left-wing governments have agreed on the same thing. The latest news is that we have also a goal by 2030, 10 years from now, to have a 70% greenhouse gas reduction. And we cannot meet that without also now trying to do the more difficult things, as Nevin was referring to, namely the heavy transport fuels. I was part of, as part of this action plan, the Danish climate action plan, a new climate act was stipulated earlier this year, And as part of that, 13 partnerships were set down by the government, partnerships that for their individual sector should come up with an action plan for how to contribute to meeting this reduction target of 70%. And these partnerships are shown here. It's various parts of our technosphere, and they are all led by the CEOs of the leading companies and organizations in Denmark. So it's really something that is taken up to the highest level possible. I was part of the aviation sector partnership, and the head of that partnership was the CEO of Scandinavian Airline System, SAS. I also contributed to the called Blue Denmark, that's the shipping partnership, and the CEO of Maersk Line was heading that, etc., etc. Food production, land transport and logistics, waste and circular economy, and the energy and supply infrastructure. I had some collaboration with all these partnerships. And they came up in March with their reports of how to meet the targets. The aviation sector a little bit later, due to problems, especially for the aviation sector with Corona, that was postponed a couple of months, but it came up with the same ambitious targets as we started up with. And those are that by 2025, the aviation sector in Denmark would like to see one plant or the production availability of sustainable aviation fuels up to 3 to 5 petajoules per year, and that is equivalent to one plant. And by 2030, up to 12 petajoules per year, which is like 25% of today's or before Corona consumption of fuels in the Danish aviation sector, including the international flights. So 10 years from now, the target is to have 25% of all aviation to and from Denmark and within Denmark run on sustainable green aviation fuels. And by 2050, the target is to be fully covered by sustainable fuels, that is 50 petajoules per year, which would be equivalent to 5 to 7 of these gas to liquid type plants. I'll show more details of that, but that is kind of setting the frame. The Danish aviation sector, actually as well as other aviation sectors in the Nordic countries, as far as that is those I know best, they have quite ambitious targets and they want to do this. Of course, they are a bit hit by the shame of flying and they are worried that they will lose customers in a larger scale if they don't do something, which is of course a good thing that they are now going very actively into this. So let's take a look of how can we do that. This is something that we should do in Denmark. And what is Denmark in terms of, I'll use a couple of slides just to briefly present to all of you what characterizes Denmark in a renewable energy supply context. Denmark is up here, as you know, in the northern part of the world. And what characterizes Denmark could be described in several dimensions: the geography, climate, and societal infrastructure, the technical part, and then other framework conditions that I'll briefly mention. Well, geography, we don't have many mountains, we don't have much hydropower, we have a very large coastline. The wind is blowing a lot in Denmark. The sun is also shining sometimes, but up till now, at least, wind power has been the more competitive in terms of when comparing to solar power. That is, anyway, changing a little bit, and some years from now, the photovoltaics will probably be just as cheap as offshore wind. So solar power, even in our hemisphere, is gaining land. In terms of societal infrastructure, we have a lot of agriculture. We produce 5 times more pigs per person than any other country. So we have a lot of manure in Denmark, and we have other agricultural residues, a bit more, or somewhat more than global average, maybe 2 or 3 times more than global average altogether. However, we don't have a lot of forest. So, and we're going to have even less. So that characterizes us. What we have, predominantly wind power and agricultural biomass, and a bit of forestry biomass and some solar power as well. On the side of other infrastructure issues, we have a very well-developed district heating grid system. We have more than 400 district heating grids, and about 60% of our domestic heating is covered by district heating. So that is a good system integrator already there, and we can use it further when we integrate fuel production. We also have a very well-developed gas grid that connects the vast majority of our country that we can also use in the future. Other relevant issues, we are interconnected with neighboring countries, and especially, of course, Norway, Sweden, where there is some hydropower, serves as a good buffer. We would, however, like to have something standby so that the Norwegians cannot completely decide the cost of the hydropower we buy for them. So we need something back up ourselves. So how do we design that energy system? Well, we need to produce some electricity, heat, and transport in a lot of variations of that, of course. And what we have is wind, solar, and biomass. So how do we design it? Also knowing that on somewhere behind this, we need also to make food, feed, plastics, and other things. How do we do that? If you take a look at the world and take a look at the issue of biomass, many of you, I'm sure, have come across the point that biomass is an attractive resource when we cannot use fossil to get our carbon for the hydrocarbons and other liquid fuels. However, it is limited. This is a picture of the green part where agriculture happens in the world, and that's also the land that is mainly suitable for agriculture. It's a third of the land area, and what we produce as an end product from all this activity is food. And what we eat is equivalent to 30 exajoules per year. Fossil energy today is 500 exajoules. And in a business as usual scenario from the International Energy Agency, we talk about 900 exajoules per year, which is 30 times more than the energy equivalent of the end product of the activity taking place on that green area. So this is a short illustration of the reason why people across all sectors are now talking about bioeconomy as not a full solution, a contributor, but a constrained resource that we should take care not to overuse. Let's take a look of how much we can have extra. A number of studies, one of the first, actually the latest consensus study by the IPCC, a working group on bioenergy, Chum et al., estimated somewhere between 100 and 300 exajoules extra potential by 2050. However, Elena Chum later says we won't say more than 200. And later studies, Laurie et al., and I was involved in one myself, but in 2014, find somewhat lower than 200. The International Agency in 2007 came up with a report suggesting 145 exajoules per year, and Slade et al. Even less, down to 100. So it's somewhere between 100 and 200, I would say, that is realistically and to some extent also sustainably available by 2050 as an extra supply that could help us cover part of our energy demands. But let us take a look upon how much does an energy system actually need, represented here by the Danish energy system. By the way, this 20 gigajoules per person per year, if we translate it to per person, it's 20 gigajoules per person per year. That is equivalent to 2 big bales of straw. That is what we have to cover all our needs for carbon in society, for energy and for other stuff. So let's take a look at Denmark. Many studies were done in Denmark. Here's a selection of 10 of the most important studies since 2006. Where researchers and other societal stakeholders produced energy system designs, all being fully renewable energy systems, using energy system analysis as a methodology for balancing demand and supply, hour by hour most often, and coming up with solutions. Each of these studies had many scenarios, So the interesting part is, what does an energy system actually need to be fully renewable compared to what we have globally available, to have an idea of the constraint related to biomass. You could go for a kind of pure energy, bioenergy design strategy, meaning that you don't change the infrastructure much, you just substitute the fossil fuels by biomass. We would then need 130 gigajoules per person per year in Denmark to supply those end services that we need to supply from our system, which is 20 gigajoules of conventional electricity demand, 45 gigajoules of heat and cooling, also heat in industry, and 15 gigajoules of mechanical energy in transportation altogether. So those are some simple key numbers. And to provide that with the energy conversion losses, etc., we would need 130 gigajoules of biomass, which is way above what is globally sustainably available. Then next step would of course be electrification, where you electrify the part of transportation that you can electrify, and you electrify the heat sector with heat pumps, to some extent a little bit of electric boilers also in industry, to the extent that that it makes sense. Here in our system design, we found that we could go down to 80 gigajoules per person per year in terms of biomass demand. It can be possible to electrify even deeper and go further down at the cost of more expenses, of course. So next part could be to introduce hydrogen. So use electricity to store electricity in a chemical form in the first step as hydrogen, but then as well react that hydrogen into the carbon of the biomass. That could be, for example, that you take the CO2 part of biogas, so you convert biomass to biogas, and the CO2 part of biogas you convert with hydrogen to even more methane. Or you could have a gasification, pyrolysis gasification of like woody biomass, and you could take the carbon from there in terms of carbon monoxide and what you get, and react with hydrogen and simply boost the energy and exergy value you get out of the carbon in the biomass. That could, in our system design here, bring us down to 55 gigajoules per person per year of biomass demand. Next step could be also to get hold of some point source CO2, could be from cement, could also be the places where you fire heat and power plants with wood pellets and so on, get hold of that CO2. And that would allow us to go down to 30. You could further use carbon dioxide directly from the atmosphere, direct air capture, and some biomass, for instance, the manure, which is a good idea to use also for climate reasons for biogas, could bring us down to 10. So now we are in the right interval. And you could, of course, go fully electrofuel using only CO2 from the atmosphere, and you would need zero biomass. We just included this to say it's possible, it's technically feasible. People are doing it across the world. Fuels are being produced in this way. Several places in the world where people take it out of the atmosphere and react it with hydrogen into fuels. Not full scale, but pilot scale, small scale, several places. It's doable, it costs a bit more. So those are the options, and the point here being that we need a pretty advanced energy system with a lot of electrification and a lot of electrolysis for hydrogen, or you could also make direct electrolysis where you transfer the electrons directly to CO2 without having hydrogen as the intermediate, but we just express it as hydrogen in our case because it's the most practically doable at this point in time. So you need a pretty advanced energy system, and that is what has led us. And this point here is not to forget about the plastics, because plastics also need carbon and hydrogen. And the plastic sector is booming. The Ellen MacArthur Foundation predict that it will double from 2016 to 2050, all the way up to 1.2 gigatons per year. And that in itself, should it be bioplastics, would require 120 exajoules of biomass to produce that. So that is an increasingly important part of the system to provide plastics. So that is the point, that we really need hydrogen. And my PhD, Anders Winter Mortensen, as part of his PhD, did this study that we have here, and you can find the article there. I think it's pretty interesting. What he did was to take these scenarios from these 10 studies and try to make them comparable by normalizing them to the same end service demands. So first thing he did was, these are studies that were conducted throughout a period of 10 years or something. So to be comparable, they need to kind of deliver into the same demand side of the system. He normalized them so that they were comparable, and then he tried to analyze how much biomass did they need, how much hydrogen did they integrate in order to lower the biomass demand, and what was the degree of electrification. So what you see on the upper graph, up here, the dots directly on the y-axis. The y-axis is the biomass needed in the system in terms of gigajoules per person per year. And those on the y-axis itself, they have no hydrogen. And it was all those studies that we found, the lowest part needed a little less than 80 gigajoules per person per year of biomass if they had no hydrogen. We designed ourselves one that could do with 60, but we believe that is the lowest we can go without any hydrogen, with a very, very high degree of electrification. So in order to lower even further from that, you need hydrogen. And on the x-axis, you can see how much hydrogen we need, how much electrolysis we need to use that hydrogen predominantly for upgrading carbon from the biomass or from CO2, and satisfy some of the need for hydrocarbons in the system using such an electrofuel power to X pathway. So what you can see is that some of these scenarios, they go further down and down. And the reason that it's not on one line is that they have different degrees of electrification, and also some differences in conversion efficiencies of the processes involved. But at the end of the day, if you go to the lower graph, we tried to identify the degree of electrification assumed by each of those scenarios, and try to illustrate how they were situated in terms of the electrification degree. So the darker the shade, the more electrified the scenarios are. It did not give a fully clear and more linear correlation, but it gave some ideas. The still lacking part of the explanation is the differences in energy conversion efficiencies of the processes involved. But what we could see altogether at the end of the day is down here. In order to get down to 20 gigajoules per person per year in the Danish energy system, we would need the equivalent of 15 gigajoules per person per year of hydrogen. Otherwise, it won't be possible. So the darker green shade area down at the lower graph here, also on the upper, that is the sustainable solution space of a renewable energy system in terms of how much biomass is available as a global average sustainably, and how much hydrogen you would need to get to that lower level and still satisfy those parts of especially transport sector, but also parts of industry and other that really, really need hydrocarbons, and that within the realistic time frame that we have for solving or meeting our climate challenge, would still need hydrocarbons. For instance, the fleet of aeroplanes in the aviation companies across the world, an airplane has an average lifetime of 40 years. So realistically, to satisfy those and not to go bankrupt, you can't exchange your fleet with electric airplanes, and that is not even technically possible either within the next 10 years, only on the very short distances and with a few passengers. So we need these hydrocarbons. And so that is a main message from this PhD. Actually, you need 15 gigajoules of hydrogen per year in order to come down to sustainable biomass demand. We think that's a good message. This is for Denmark. However, it is not that sensitive to regional differences. We don't have as cost efficient solar power, but we have wind power. But what is really determining this at the end of the day is the need of liquid fuels for aviation, long-going ship transport and heavy trucks. We don't need much in this system for electricity backup or for heat or for anything. That has been eliminated by electrification. So it is a pretty robust also to extrapolate this to a more global level. Right. So that was an introduction to the part that has to do with our gas to liquid fuel, because the reason we arrived at pointing to this solution as opposed to other pathways is the way, the elegance of how well it integrates hydrogen and how well it is a system integrator all in all, and thereby contributing to reducing the demand for biomass in the whole system. Moreover, it's a very mature technology that we depend on in this pathway, with a technology readiness level of like up to 9 in most of the system parts, 8 for some of them, but really, really mature, and many of the plants really existing several places in full scale. I will come back to that. The study here was conducted together with the Nordic Initiative for Sustainable Aviation, NISA, and NIRAS, a consulting company in Denmark. And it was paid by the key stakeholders that is shown here below. So basically, it looks like this. A first step in the system, a kind of a backbone, is biogas. Biogas is a facility, it has a growing significance in Denmark right now. It's really expanding. That treats manure and other agricultural residues, second generation biomass from agriculture. And also it handles biological waste, and it's a waste handling center in our society. It does so in a quite elegant way because it helps agriculture reducing their own climate greenhouse gas emissions from manure, because when the farmer has an incentive to supply a biogas plant with manure and straw, the manure stays much shorter in the stable and in storage, and you have much less greenhouse gas emissions. It's really, really significant, that reduction that is the consequence of a biogas facility taking the manure from agriculture. Furthermore, the biogas facility enables managing the manure, the fertilizer value, nitrogen, phosphorus, potassium, and to some extent sulfur, but also the carbon content of the digestate, which is the degassed manure, that goes back to soil. And the biogas facility can manage and manipulate the manure so the farmer and the individual field gets a designer fertilizer back that matches the demand of that specific field the best possible way. So that is an optimization facility that really benefits agriculture as well. And part of the elegance here is that soil needs carbon as well. And we energy system analysts, we often forget that. And we try to assume that there is a certain biomass resource available for our energy system. And later on, we then consider how should we use it. We shouldn't do it like that, because how much is available for our energy system really depends on how we use it. Because if we, for example, use it for biogas, we give back the hard degradable carbon to soil. So the soil carbon content on the longer term stays almost the same as if we had plowed down fully, for instance, that straw biomass instead of using it. Whereas if we take the straw from the field and just burn it, no carbon goes back to soil. And the farmer on the longer term would want to plow down some of the straw without making it available for the energy system. So we should consider that. And what biogas does is that it makes actually 100% of the carbon that we take from the field, from the soil, it turns it into methane, a very high exergy carbon compound. So we start up by producing something that we can put on the gas grid at 100% carbon efficiency, which is a really important issue when biomass and carbon from biomass is a constrained resource. So on the gas grid, we can store it, we can save it for months, and we can take it up at another location, and we can put it into a gas to liquid factory that converts methane into liquid, longer chain hydrocarbons and alcohols as well, to some extent. Such a technology and such a factory exist already several places in the world, in Malaysia, South Africa, Qatar, Nigeria, and other places, and has been there for many, many years. It is a process, two-step, a steam reforming, converting methane into syngas, hydrogen and carbon monoxide, and then converting the syngas through a Fischer-Tropsch so-called process, invented by Fischer and Tropsch, some Germans, in 1923, I think it was. So it has been well known for many, many years, and it's in full-scale operation for many years, owned by Shell and South African Sasol and others. So, so this is something that is directly implementable just using biomethane instead of what is used today is the natural gas, off gas from oil extraction facilities, remote places. And you can convert that into crude oil, and you can refine that crude oil into aviation fuels, other fuels, and even naphtha for plastic production. But it doesn't end there. The benefit of this pathway is as well that the CO2 of biogas is probably the easiest and most accessible source of CO2. And it's easily convertible by hydrogen, because that is what the biogas, the methane forming microorganisms already do, because this is their living. They convert CO2 and hydrogen in the biogas plant to methane as the last step of a big chain of events happening there. You can feed it with more CO2 and more hydrogen, and you can design a plant that will just convert that as well. So it's a place where the technology is already there that allows us to integrate CO2 and hydrogen into our system, producing hydrocarbons. And you can avoid making heat from electrolysis, if it's an alkaline at least. And also when reacting CO2 and hydrogen, you do get some heat, and you can locate that on the district heating grids. And the biogas allows you to go to the medium-sized district heating grids and utilize those for locating this and making use of almost all the process heat formed here. Furthermore, you can take the gas grid, and you can sometimes, when the wind is not blowing and sun is not shining enough, you can produce electricity in a very cost-efficient way in a gas turbine using the gas that you have stored. And that is a fantastic way to balance the fluctuating electricity supply. And you can also, in the gas to liquid facility, integrate even more CO2 and hydrogen, because that process also exists. It's called the reverse water gas shift process that converts CO2 and hydrogen into syngas again. That can then also enter into the Fischer-Tropsch production unit and produce liquid fuels. So it allows you to really boost the backbone of the system with CO2 and hydrogen and get as much as you like. And that also produces heat, and these are giga type of plants, so they will be located in the major cities with the big district heating grids. And finally, of course, you will prioritize producing hydrogen by electrolysis when the electricity is the cheapest, and the more wind power and solar we get into our system, the cheaper, the longer periods we have with cheap electricity. And it turns out that for quite a big part of the time, we have quite cheap electricity at the end of the day. So it helps the system here as a backbone, helps both taking the peak electricity from wind and solar and supplying when you have no electricity. So it is actually a full balancing. If you look at proportions and scale of it, it's a full balancing of the electricity system. You really don't need batteries or any other electricity storage, except on the outskirts of the system with the very small distribution grids. If the individual houses have both battery cars, solar cells, and heat pumps at the same time, we might have an undercapacity of the smallest distribution grid, that where you could have an idea of some kind of storage on the most significant knots in the system where you have your capacity issues, but not as a full system balancing. You really don't need it if you have a fuel production pathway like this. And also on the sufficiency side, because a really important issue when we talk about fuel supply pathways is to talk about sufficiency. It doesn't really make any sense that you can make a fantastic fuel if it's not a solution to the challenge, which is to actually provide a solution to climate change problems on full global scale. Denmark is emitting 1 per mil of global greenhouse gases, and that we come up with a fantastic green solution that cannot be scaled up, it doesn't really make any sense. What we need to produce in Denmark is a model for the world to follow. And this is it. So the biogas potential in itself has an upper limit in Denmark at 90 petajoules per year. And that should be seen in relation to the demand side. We only need 5 petajoules per year, and that's a maximum for electricity grid balancing. It's really small. We need 15 petajoules per year for industry. That is the 25% of industry that cannot be electrified. We would want some fuels for that. And we need 50 petajoules per year as aviation fuels. 20 for long distance road that cannot be electrified. And it's difficult for this shipping because we have Maersk Line, they have 20% of the world market. So if we look at them, it's 500 petajoules per year. The domestic part that is in Danish waters is only 6. But of course, we import a lot of goods from China and other places. So our consumption related part of the fuel demand is probably like 50 petajoules per year as well. And plastics, we would by 2050 need 20 petajoules per year consumption based, I would say. So if you look at that and you realize that you have conversion losses as well, the 90 petajoules per year of biogas is not nearly enough, of course. Then we can hydrogenate the CO2 part of biogas. That would bring us up to 160 petajoules of biogas per year in Denmark. And that is just about this, that is the same as the end demand of these hydrocarbons in transport industry and electricity balancing. However, we have serious conversion losses for heat as well. It's unavoidable. So we don't have enough either here. We need more CO2 and hydrogen in there. And that's when we start using CO2 as feedstock. If we take flue gas from waste incineration, we could go up to 200 petajoules per year. It's still not fully enough, but we're almost getting there. And that has the nice side effect that if you take CO2 from waste incineration and you produce naphtha as equivalent to the fossil fraction of that, you will have a completely closed plastic system as well, with absolutely no CO2 emission. So whatever you cannot recycle mechanically of plastics, you can burn, capture the CO2 and produce new plastics, and you have closed the system. We're pretty close to doing that. We talked with Lego and other Danish big plastic producers, and they're pretty interested in this idea as well. So I think that will come. And then if you start including CO2 from biomass incineration for CHPs and other, you will look at 350 petajoules per year of equivalent input to the gas to liquid factory. That includes the hydrogen part, of course, and that is now enough. And then you can also capture CO2 from the atmosphere, and you could go all the way up to close to infinite. Of course, then you're limited by the electricity production, but not by carbon when you start using the atmosphere. So the point being here is that we have a sufficient pathway, sufficient and sustainable, because it's a really good idea to use biogas and biomethane. It's the cheapest, and it's a very sustainable thing for agriculture to have that in the system. And it's a fantastic pathway for integrating, assimilating CO2 and hydrogen into the system, because technology-wise, this is already there. And then it helps balancing the fluctuating, both in terms of peak shaving and providing when there's nothing. And it provides fuel for industry as well, and it can close the plastic cycle. So all in all, it has pretty interesting system integration aspects. Moreover, you can also go directly from the biomethane, liquefy it into liquefied bio-LNG, sail your ships directly on that, maybe even run trucks on it. Or you can produce bioelectromethanol directly from the biogas, also integrating hydrogen there, and use methanol also for transportation. And you could go pyrolysis on the non-degraded part of the fiber from the biogas in the digestate. If the agricultural field has more than enough carbon, it's an option to also take part of that carbon that is non-degraded and do pyrolysis and produce more fuel. So it, in a very nice way, it integrates some of the other fuel pathways as well. Cost-wise, I have 5 minutes. Cost-wise, we found that it is more expensive than fossil fuels, but not necessarily that much more. The dotted lines represent the lower and the upper cost limit for fossil fuels in terms of gigajoules, euros per gigajoule of jet fuel from factory. And we are a bit above that when you have the biomethane feedstock. If you use both bio and electromethane feedstock, you are higher because of the cost of the hydrogen becomes a bit higher to have the electromethane as well as the biomethane. And then we have the pure electrofuel. This is a co-electrolysis type where you have a co-electrolyzer converting CO2 with steam under high temperature and pressure directly into syngas. And that is the SOEC type of electrolysis, solid oxide electrolyzer cell type, with a much higher efficiency than we assumed for the electromethane part. So that is why even cheaper here, looking at 2030, where we assumed that that technology would be available. That's the most uncertain part. But having that electrolyzer technology would also make the electromethane cheaper. So they would be quite comparable. So those are the costs. But there is, however, even a more story to tell about this, because in a very highly renewable scenario in Denmark, as well as neighboring countries, where you would have also Germany, England, other neighboring countries having a lot of fluctuating power. This is a scenario developed by the Danish transmission system operator Energinet together with other European transmission system operators, NSOE, that organization by 2018, a scenario they call global climate action, being the very high end. And the gray curve you see, the x-axis is a year, the hours in a year, is the electricity price variation in this scenario. And you have a lot of low prices and a lot of high prices. And the duration curve is the blue one. And what you see to the right is that you have a little above 2,500 hours with very, very low electricity prices, because you have so much wind power and solar in the system. But you also have like 3,000 hours with very high, and this is twice today's offshore wind power prices that you'll have in those hours. So with such a curve, it becomes pretty interesting to have a flexible feedstock for such a gas to liquid. So in the very low price hours, you would of course use electrolysis and have hydrogen and CO2, and in the very high price hours, you could use your biomethane and in this way optimize. And the capex part of investing in steam reforming for the methane conversion and reverse water gas shift for the CO2 and hydrogen conversion is pretty low. It's less than like 15–20% compared to the operation, the OPEX cost of buying the biomethane and buying the hydrogen. So that extra investment does not really disturb the cost optimization. So a flex solution with biomethane, hydrogen, CO2 is really economically advantageous in a very high fluctuating renewable electricity type of scenario. And this is a student project, so I should make some precautions. I did not check this up myself. It was made together with Energinet, and they were very good students, but we need to check it up further. I just mentioned it as a hypothesis here, that actually looking at some of the ways to produce this gas to liquid, the middle four in this, you will see that the cost in such a highly fluctuating, high share of fluctuating electricity, you could actually get below the higher end, the upper end of today's fossil fuel price. for jet fuel. This is pretty interesting. So how does the world look? I will use one more minute, Nevin. Funen, this is the island where I live, where the University of Southern Denmark is located, and it's the island of H.C. Andersen. In the middle there is Odense. The blue part is the district heating grids. The red lines is the gas grid. And this is kind of a fairy tale being here in H.C. Andersen's home. First, the world, I want to illustrate how the world can look using Funen as a model. So we need to be connected. Everybody needs these days to be connected, and our power will predominantly come from the North Sea. We need to make biogas from residual agricultural biomass and CO2 and hydrogen out there. And we need 10 of those facilities on this, and we are 10% of Denmark. So in Denmark, we would need 100. And they will be there and be agricultural management residue facilities, giving a lot of benefits to agriculture. And the process heat of doing this will be then put on the local district heating grids, and the size of that is just very well suited to take this magnitude of process heat. Bio and electromethane will then be put on the gas grid and transported into the central facility. Electricity balancing can be located centrally in Odense. When the wind is not blowing, we have that now, the gas available. Fuels and plastic are made then from the methane, CO2 and hydrogen, located in a large scale facility in there, using a lot of CO2 from waste incineration and maybe whatever they have in there of CO2 and more hydrogen, and the heat will be placed on the big district heating grids. And all these electrofuels that comes out of this, they are actually, we don't need taxpayers' money, because the aviation sector and the plastic sector, is our experience, they are willing to pay that extra cost. It doesn't really matter much. Your flight ticket will only increase like 20–25%, and it will still be cheaper than it was 6 years ago. So it's not changing the world dramatically. The plastic in your computer, if that was made of CO2, would increase the computer price by 2 per mil. And of course, we will earn a lot of money by visiting delegations from China and other places when showing this world. So what does it cost? Well, the Danish Energy Agency, one of those studies I mentioned, estimated 1.5 billion euros extra per year. That is equivalent to 0.5% of the Danish gross domestic product. That's the extra cost compared to a fossil system. That's 20 euros per person per month. That's the same as a Netflix subscription or a Fitness World subscription. It's equivalent to like 5 euros per week, and that is what the cost of a cup of coffee is at Starbucks. So the cost of getting a world like this, very supply secure, everybody has access to water for hydrogen, wind, solar, and CO2. It's CO2 neutral, and it'll cost you a cup of coffee per year. So that was the end of my presentation. Sorry for taking 4 minutes too much.
Thank you, Henrik, for a very interesting presentation. I will now open floor for discussion and for questions. The rules are following. Please raise your hand in order for me to see you on the top of the participant list. We already have Laura Vanoli asking for a question. And you can also write your question in questions and answer area. So please, questions. Laura, you will also need to unmute your microphone once you get the microphone. Or was it an error? Laura, do we hear you? Okay, so probably no question from that side. While we are waiting for questions, I will put some of my questions. So you said that in one of your slides that it will depend on the price of hydrogen. What is the price of hydrogen that you are thinking of? Current price of hydrogen, or we are expecting it will fall down?
Well, in our present situation, looking a few years ahead, we based it on an electricity price of, I think it was 5 cents per kilowatt hour, and a conversion efficiency of 70%. So I'm not completely sure what it makes, but that is at least the base case. Used 5 cents per kilowatt hour of electricity.
But you have shown that in 6,000 hours, the price of electricity will be lower.
Right. In a more distant future, with a very high degree of fluctuating electricity and a very large share of fluctuating, which I personally find realistic that we are going to get there. Yes, it will be lower.
Can you comment on plans in Netherlands and UK to use hydrogen for heating or e-methane for heating? They want to put it into grids and use it for heating. Do you find that having any sense?
Nah, I mean, knowing London, of course, I do see some challenges compared to a Danish major city with district heating grids and so on. But no, I mean, it's really problematic because, I mean, yeah, of course, if they make methane from CO2 they take out of the atmosphere and react with hydrogen and use it for heating, well, it's going to be very costly. And of course, windmill farms and solar cells also take up some space. It's really, really problematic to think hydrocarbons and also hydrogen for heating purposes when you can use electricity directly. It's really a detour.
We are still waiting for, thank you for this answer. I fully agree with you about that, but there's seriously pushing it towards that direction. I'm trying to understand what is behind it, but apart from seeing a gas lobby behind it, I don't really understand any sense in that approach. I'm still waiting for questions. Florian, what is with, can they actually put questions? Are they unblocked? No, no questions. So
Laura is unblocked.
Okay. Laura, do you want to put question now?
You have to unblock your microphone on the left downside of the Zoom session.
The host of the meeting should be able to unblock as well.
As well, yes. No, I'm unable to unmute her. Can you unmute her? Okay, so there is yes.
Now Laura Vanoli is unblocked and the microphone is on. Or what? No.
But there is a question from Felix Meyer in the question.
Yes, there is a question from Felix. While we wait, Laura, please unblock Felix, give him a microphone. Felix, the screen is yours, or the sound is yours.
Or we can read the
In the realm of life cycle assessment view, by how much is the CO2 intensity of the future system that you proposed reduced? After all, also renewable energy systems have carbon footprint, especially biogas plants.
Well, biogas, well, first I can say CO2 intensity is reduced significantly. It will depend on the background system that is where our energy system is residing, because of course for wind turbines you need to produce them. If parts are made in whatever country, United States, they have some carbon footprint with them, etc., etc. But at the end of the day, I think the most important question is, by 2050, which is where we would like to be fossil free in Denmark, what would be the system with the lowest carbon footprint of all? When you have no more fossil fuel, the biomass will carry with it some carbon footprint if it's not a very sustainable biomass. Manure does not carry with it a carbon footprint if you use it for biogas, because you reduce more than you create. So actually it comes with a negative carbon footprint if you take as a starting point that the manure is there in any case, the animal production is there in any case. Then you reduce it by using it for biogas. So the biogas facility does not lead to extra CO2 demand. On the contrary, to a quite significant reduction. You can then argue if the animals production is sustainable at all, of course. If you use straw for biogas, you will reduce the carbon footprint compared to fossil fuels by more than 90%, 95%, I'm sure. So at the end of the day, I think it is realistic to reduce carbon footprint from the whole system by something like 95% by 2050.
Okay, thank you.
I've been doing life cycle assessments for 25 years as well, and that is kind of my meta message and understanding.
Okay, thank you. The next question is from Mr. Jukic. He didn't raise hand, so can we find him, or shall we read the question? He's allowed to talk now. Mr. Jukic, can you talk? You need to unmute yourself.
Can you hear me now?
Yes.
Yes.
Yes, hello, thank you for your presentation. I have a very short question. Can you explain, please, the status of natural gas to 2015? And if we will stay to balancing, for example, of electricity, such as you told from your presentation, and in which percent of the total consumption of energy in the Denmark? Thank you.
But by 2050, for sure, it will be almost no natural gas, but biogas. So what we talk about for balancing the electricity system is biomethane, not methane from natural gas. And the benefit of using the gas grid is that you can gradually replace your natural gas with biomethane from biogas, and also electromethane from biogas. Today in Denmark, I think we have by now substituted 20% of our natural gas by biogas. And we have the potential in Denmark to produce more biogas than the equivalent of our use of natural gas today. So we have no problem whatsoever in Denmark of fully replacing natural gas with biogas.
Thank you. Thank you.
Fully replacing, that's quite a big amount. What about the sustainability of the full replacement of natural gas?
Sustainability, do you mean climate-wise or what?
I mean biomass-wise. Biomass has a certain sustainable potential.
Right. If you take manure only, in Denmark, let me start another place. We use 20 petajoules of natural gas in Denmark today. Sorry, 100 petajoules of natural gas in Denmark today. Making biogas from manure, the upper potential is 20 petajoules, but including straw and industrial bio-waste and domestic bio-waste, etc., we can have all the way up to 90 petajoules. If we also then react the CO2 part of the biogas with hydrogen, we can have up to 160 petajoules of biogas. And natural gas was 100, right? And it's going better and better in Denmark in terms of avoiding methane emissions from the biogas facilities themselves. We are, at some point, we had like up to 4% emission of the methane, but now we're looking at somewhat like below 1%. And I'm pretty confident that we can reduce it to much less than 1% emission. So in our country, I don't think that the methane emission from the biogas facility itself is going to be detrimental to a biogas strategy.
Well, if you use methane for heating, then 2% fugitive emissions makes gas as bad as coal.
Right. I'll be surprised that you talk 2%. I would maybe think 4%, but yeah.
Okay.
But you're right. Yeah, 4% emission is a lot. But
it's a lot, yes.
But I don't think you would find 4% emission in a Danish infrastructure.
Well, it's more with natural gas extraction where it happens than in biogas production, I suppose. We did calculation for Croatia, and we came to 10% of sustainable biogas potential compared to natural gas consumption at the moment. So I was a little bit surprised at what you say, but it might be because you have lots of manure.
We have quite some manure.
Quite some, yes.
But this agricultural straw residues actually can give us like 45 petajoules of biogas, whereas manure can only give us 20. So straw residues and deep litter.
So you're not counting here on energy crops at all?
No.
Additional energy crops just for biofuels?
We don't want energy crops in Denmark.
No. Okay. Yeah, that makes sense. Okay. Any more questions? Since I don't see any more questions coming out, then I would like to thank you very much, Henrik, for your excellent lecture, and I hope that we will soon start developing e-fuels so that we can actually see how they work in reality, slowly. And then probably after 2030, we should go much faster.
Yeah, the first two projects are trying to get started in Denmark already. So, very big project in Copenhagen led by Ørsted and Maersk and others.
I have one more question. What about aviation? You worked on aviation fuel. What are the steps that you would have to do in order to have it certified as internationally acceptable fuel? So when can you actually start filling in international planes with such a fuel? How far are we from that point?
You can already do it. The Fischer-Tropsch pathway is already certified up to 50% blending using coal as the feedstock. And using biomethane and CO2 and hydrogen gives an even cleaner fuel. So I don't think it's an issue. It's more a formality, but that formality might take a couple of years. So, but the aviation sector experts I talk to, they are very confident that this is only a formality. Technically, there's no issue. It's the same fuel basically, but there might be a little less aromatics in there. That can be a problem to some O-rings in the motor and so on. They need aromatics for being completely tight. But it's some technical issues that you can deal with by some chemical additives and stuff.
So basically by 2030, you think it could be put into process?
Even before, 5 years
Even
from now.
before. Okay. Thank you very much once again.
Yeah.
Do we have more questions? Okay. We have another question. I will allow it because we were a little bit late with lecture. It's from Sheer. Florian, can you give a microphone to Sheer, please? Sheer, do you hear us? Can you speak?
Yes, I can hear you. Thank you for the presentation. Exactly on this point on aviation, I was curious a little bit more. I read that also at the European level, the Flight Path 2050, Europe's vision for aviation, also emphasizes the possibility of liquid fuels and the energy from sustainable biomass. You mentioned a little bit with Nevin's question, but could you elaborate a little bit more on this point? And also, how do you see this possibility, given that the EU strategy for energy system integration includes low carbon fuels, including hydrogen, for hard to decarbonize sectors, and it mentions the aviation sector? Thank you.
Yeah, I mean, I understand your question as you want me to comment on making liquid fuels from sustainable biomass. I agree that you can do that, but there's if you really look into the quantity of sustainable biomass that you have available globally, it's really limited. So going for that, I know there are liquid fuels produced from waste oils, from food processing oils, and from other types of vegetable oils and plants. Problem is that it's really insufficient. And the challenge of that is that it's kind of delaying the process of finding something sustainable when large initiatives for purely biomass-based fuels are taking up the political agenda. Then nothing else tends to happen in that period of time. It has been the problem in the European Union for a couple of decades now, that the biofuel exclusive impression lobby has been so successful with blending requirements of biofuels that we are not even close to having a sustainable solution. Sufficiency is really, really important, and you cannot have a solution to the fuel supply without hydrogen and without involving CO2 from somewhere reacted with hydrogen to reduce the demand for biomass. So I would say any pathway needs to look at carbon conversion efficiency and how well it integrates hydrogen, besides, of course, the cost side and the other issues I touched upon. So fuels from sustainable biomass is at best insignificant, and at worst, it becomes a problem of delaying real solutions.
Thank you for the answer. I would now close the floor for questions, and thank again Henrik Wenzel for excellent session, and thank to participants who were with us. I would like to invite all the participants to come to the closing session, which will start at 13 hours sharp. And with that, we will close this live part of the conference, but virtual conference is continuing the full day tomorrow, so participants can continue to answer the questions that they received. Thank you very much.
Thank you.
Thank you.
Bye-bye.
Bye.